Today we want to talk about vector operations. These are the things that we can do with vectors. Whenever you learn about a thing in math, you have to learn what kinds of things you can do with that thing. What kind of operations can you perform on those things? What do we mean when we say things like add, subtract, multiply, and divide? And so that's what we're on about today. We want to talk about the vector operations. So our first one that we need to know about is vector addition. Vector addition is an operation that works exactly like you think it would. I'm going to ask you to add u and v, and you're going to do exactly what you would do if I told you to guess how vector operation works. So this is in the category of works like you think it would. And that's always good. Whenever there's a math thing and you're faced with what to do and it works how you guess it would work, that's always best. That means it's a well-designed operation. So if, for example, I wanted to add u and v, first of all, I write it like we think we would write it. So take 2, -1, 3, plus 0, 4, 1. What's going to be our first entry in the u plus v? 2. What's our next entry in u plus v? And our last entry? We just add the corresponding component. So the sum of vectors is equal to the sum of the corresponding components. Sum of vectors is equal to the sum of the corresponding components. That's just what you guessed you would do. 2 plus 0. -1 plus 4. And 3 plus 1. Just find the sum of the corresponding component. If the vectors aren't the same size, you don't get to add them. It doesn't make sense to try to add them. So vectors must be the same size. So I couldn't take 2, -1, 3 and add it to 4, 5. This vector addition is not defined. Four, 5 is not in the same space as 2, -1, 3. 4, 5 is from R2. 2, -1, 3 is from R3. It is very important to realize that R2 is not a subset of R3. It's a completely different thing. R2, elements of R2 are not also elements of R3. They are completely different spaces. We could say that R2 is isomorphic to a subspace of R3. And we could even use the XY plane to model that. But that is definitely not the same as R2 being a subset of R3. If you are in R2, you are not also in R3. So R2 is not a subset of R3. No matter how we're writing them, if I write a vector that says 2i minus 1j plus 3k, I don't get to add it to 4i plus 5j. If it said 4i plus 0j plus 5k, then they're in the same space and we can add them. This is why ijk is a little bit weak. You have to know where your vectors are from, because we wouldn't write a zero term. So that's a good question though, because if I had written 2i minus 1j plus 3k. Yeah, if we have, and then 4i plus 5j, because we can write 4i plus 5j, and it's unclear whether that's from R2 or R3. Does this have a 0k? No. We can't assume, so it's not about adding a 0k. We can't assume that there's a 0k there. We don't just get to look at this and say, do we need 4i plus 5j plus 0k? Now, if I wrote my vector, if I had a different vector, if I say I wanted to take 2i minus 1j plus 3k and add it to the vector 6i minus 3j. Now, if I want to make sure that this vector is in R3 and I want to decrease any miscommunications, all I have to do is write plus 0k. And now I've told everybody this vector is in R3. You're just supposed to know. It's always a bad plan to just assume that your reader will just know what spaces things are in. If you can increase clarity, then you should increase clarity. But I fully get that sometimes you just want to do some shorthand. Any questions? This is when we're speaking a precise language like math, and it doesn't apply to imprecise languages like English. So if you're like, oh, can I go to the bathroom? Then your teacher should not be like, well, I don't know, can you? Because when in English you say, can I go to the bathroom? That is equivalent to, may I go to the bathroom? Can I have permission to go to the bathroom? When someone says that, you know what they mean. Don't be a dick. But when you're talking about math, you want to make sure that there's clarity. And if I just drop these two vectors on you, there's nothing that where I've indicated that these vectors are both from the same space, and I'm just saving myself some ink by not writing plus 0k. Now, if I had said let u and v be vectors in R3, and then wrote 4i plus 5j as v, then you just say, well, just said that this is an R3, so there must be a 0k. But if you don't have any kind of clues as to where something is, maybe you should increase your clarity. Does that make sense? You fail to do something like this, and I just take off 1 billion points. And you go all the way back to elementary school, and 1 billion points. You go all the way back to elementary school, and you have to do all of that twice. I'm just kidding. It's 3 times. So you have to go to elementary school through high school, then go back to elementary school and level up again. I'm just kidding. That would be ridiculous. So in vector addition, it works just like you would guess. You have to make sure that the vectors are the same size for addition to make sense. There's a geometric interpretation of vector addition. As long as there's something that indicates that I hat plus j hat plus 0 k hat, or 0 I hat plus j hat plus k hat. As long as you there's something in your statement that says these are vectors from R3, and this first one, this jk one, has a 0i, and the ij one has a 0k. But if I just wrote down 5i plus 3j, and then wrote down on the next one 7i plus 5k, or 7j plus 5k, we're not really sure if we can work with that. I would not want to ask that problem on its own without saying these are vectors from R3. So if you don't see one of the letters, it's a 0. We need to have a geometric interpretation of vector addition. So when we want to interpret the sum, if we want to picture the sum of a vectors of u plus v, let's say, we draw the vector u and we draw the vector v at the end of it. So this is like a tail to head method. We draw the vector u and then we attach the v to the end of u. And then u plus v will start at the beginning of u and end at the end of v. This is how we interpret u plus v. We should note that this is the same as v plus u. If I drew the vector v and then attached the vector u, we would end up at the same place. So if I draw the vector v, and then to the vector v attach the vector u, yeah, up and right, or to the right and up, both work, just like rise and rise over run. So u plus v is equal to v plus u. Vector addition is commutative. This is good. When we have an operation that we want to call addition, it kind of needs to be commutative. Commutative is the order. U plus v is equal to v plus u. We can see that this was going to be the case when we talked about how we add vectors. Vector addition is based on just adding real numbers. So it makes sense that t plus 0 is the same as 0 plus 2. So it works out that way. And in our geometric interpretation, where we're making the diagonal of a parallelogram, we can see that u plus v is the same vector as v plus u. Vector addition is commutative, and that's good. Vector addition is commutative. If you're inventing new operations and you want to call one addition, this should be commutative. Any questions? Vector addition works just how you think it will. Second vector operation. Commutative. Oops. In very lazy professor fashion, I refer to this as scalar multiplication. Specifically, it's scalar multiplication of a vector by a scalar. Or scalar multiplied by a vector. This is also in the category of works how you think it would. What do you think the first entry in 5u is? If u is 2, -1, 3, what's our first entry in 5u? 10? What's next? -5. And next? 15. Perfect choice using the question inflection because I'm saying it's work how you think, how you guess it would work. So you want to make it sound like you're guessing. Okay. Yep. Just how you think it would work. If we multiply by a negative, well, we're just multiplying by a negative number. It doesn't change how we do things. We're just going to multiply the corresponding components. So 2 times -1/2 is -1. -1 times -1/2 is +1/2. 3 times -1/2 is -3/2. I gotta throw a fraction in here, make sure everybody's okay with fraction. I don't know how you use only the calculus that still hang on fraction. Some people do fraction. Decimals all right, but some of our decimals aren't very good because we went with base 10. Like 1/2 works out great, 0.5, no problem, it stops, but 1/3 is like 0.3 repeating. That's really annoying. Yep. Plus, sometimes the repetition is very long, like 0.3 repeating is not really a big deal, but 1/7 is 142,857, 142,857. That's kind of annoying. The nice thing is every time you divide by 7, you just start off at the next one. So if it's 1/4, I think it's 142,857. But then 2/7, you just start off with the next higher number. So 2,85714. And then 3/7, the next higher one is going to be the 4. So 428,571, and then so on. All you have to remember is 142,857, and then know that it is. These are the kinds of things you have to think about if you play D&D in my campaign. Player in my campaign, and the puzzle is probably going to involve math. Usually it involves counting, which means it just evolves into combat anyway, because my players be like, well, how are we supposed to know what base 7 is? I'm like, well, I don't know. That's why you had to fight the golems. Well, you're going to have to fight the golems then. I don't know. Our geometric interpretation for scalar multiplication is unsurprisingly scaling. That's why we call them scalars. They stretch vectors or squish vectors. The important thing to note here is that they don't change the direction of the vector. They might reverse the direction of the vector, but that's all still on the same line. They don't move things to a different line. So if I have the vector u, then the vector 2u is going to go in the same direction, just be twice as long. It just says stretch or squish. Highly technical terms. This is why I don't get to come up with terms for things. What should we call this? It's a squish. If we multiply by something bigger than 1, then we're going to stretch our vectors, make them longer. If we multiply by something less than 1, but still positive, we're going to squish our vectors and make them shorter. If we multiply by a negative, it changes the direction to the opposite direction. But all this is happening on the same line. We just stretch or squish along that line. How's everybody okay? Or it's just how you think it would work. Vector addition and scalar multiplication are our most basic of vector operations. With these two operations, we make linear combination of vectors. So here's a linear combination of the vectors u and v. Think of using the u and v as your Legos, and 2u minus 3v is a kit that you can make out of the u and v Lego. If I take 2 of the u Lego and negative 3 of the v Lego, we can figure out what the kit is going to look like. And it works just like you think it would work. The order of operations is still in effect. I'll take care of the multiplication first. It is critical that you don't think of this as distributing the 2. The only person in the room who would care is me. I might be the only person on campus who cares to call this distributing, but I will. And if you're like, I'll distribute the 2, I will take off massive amounts of points. Because 2, negative 1, 3 is not separated by some operation over which we distribute multiplication. We're just multiplying the vector by 2. It's not distribution. We're also writing an awful lot more than we normally would. We would just think about what these numbers are and write down the answer. 4 and 0 is 4, negative 14, and 6 minus 3 is 3. I didn't distribute. Minus 1,000,000 points. I multiplied the second vector by -3. And so I wrote, when I started writing this -12, I'm like, oh crap, I have to write a plus. So we multiply by -3. So we're adding the opposite. That's true, but I overheard it. So I gotta be like all Big Brother. Big Brother is always watching. A linear combination of U and V. It is a little bit weird that I do that, and someone always asks that question when I multiply by the -3. I mean, that's just not how like normal humans would do this. I really gotta up my game because we would write, if we were even gonna write this down, we'd probably just use the multiply by 3 and then subtract. We're making a linear combination. Anytime you're making a linear combination of things, you're using vector addition and scalar multiplication. So dang it. I knew I should have just made them both positive. I don't know why I didn't just go with +7 and +12. I thought I can totally do this in my head, and I just totally can't. So I'm just going to write it down. It's a +3 and a -4, right? So E is going to be e to the -3t, and y2 e is equal to e to the 4t. Now, if you haven't been through differential equations, that's okay. The point is I have these two different solutions to this differential equation. That means if I take the first derivative and second derivative and combine them in this way, I will end up with 0 for these two different functions. So our general solution is a linear combination of these two functions. Where we multiply each one by some scalar and then add them together. So linear combination is a more general concept, but it's just a combination of vector addition and scalar multiplication. How's that, okay? That's DVD bonus material. It comes from differential equations. If you haven't taken differential equations, that's totally okay. This is a reference that you have later on. You go back and watch the MCU in chronological order instead of release order. You'll be like, oh, I get that reference. Or if you read all the comics, you can tell everybody all the differences between the movies and the comics. And your friends will think you're insufferable. Yeah, your friends wouldn't think you're insufferable because you wouldn't have any friends anymore. It's like if you really like Star Wars. You might be friends now, but keep talking about Star Wars. Eventually, you're going to disagree on someone, disagree with them on something. Like you never like, oh yeah, we love Star Wars. It's always like if there's like more than one person, but we love Star Wars for now. Because they might have a horrible opinion about Star Wars that makes them wrong. But remember, they're thinking the same thing about you. This is why the greatest movie franchise of all time is, of course, the Fast and the Furious, because we can all agree that those are the best movies. Any questions? Not on the Fast and the Furious, but or not on Star Wars either, on my vectors. Incidentally, it was when Fast 5 came out that I said Fast 10 will be in space. Now you're thinking, hang on a second, it was Fast 9, wasn't it? I'm like, Hobbs and Shaw. 9 is 10. We got some Roman calendar shit going on, but I still maintain I was correct. I think the next one has Thanos. I think that would be awesome. Fast and Furious, Infinity War. I have the Infinity Stone, but I've got family. Perfect. He like crashes a car into Thanos. I'm inevitable. Yeah, but that's a 1969 Dodge Charger. What? And instead of snapping its fingers, it just turns over. And then we start going in the dust. Call me, Marvel. We'll talk. You'll have to lift that restraining order, but call me. What are we talking about? I like how in the Fast and the Furious movies, you could be a villain in the Fast and the Furious movies, which means you're going to be on the team in the next one. That's just like how it goes. Like whoever the villain is, it doesn't matter what you did. You can lead literally out to destroy the world. But in the next one, you'll have had dinner at Dom's house and you're going to be on the team. Everything's cool. It's like, well, didn't that guy try to destroy the world 2 movies ago? It's like, well, yeah, but then he came to my house and we had barbecue and Coronas. Sorry, Mr. Diesel, make sure the label is facing the camera. Oh, sorry. And we had barbecue and Coronas. Corona doesn't return my calls either. I'm like, I'll drink a whole 6-pack every class. Then they're like, oh, won't you be extremely drunk by your 3rd class? I'm like, oh, no, because it's Corona. I went to college. More importantly, I've been kicked out of colleges. So. All right, last thing today is just going to be a lead in to the next one. I need to roll credits for a little while. This would be the mid-credit scene. Now, the post-credit scene is just a tag on, like, just random stuff happening that's supposed to be funny. The mid-credit scene, that's where we preview the next thing. So this is going to be a mid-credit scene previewing the next couple of days. We got 2 kinds of vector multiplication. There's 2 kinds of vector multiplication. I'm going to follow the same numbering system. There's, go ahead. That is correct. We got 2 kinds of vector multiplication. This is where we have a vector times another vector. We've got 2 kinds. The dot product, AKA the scalar product. Or the cross product, which is the vector product. But here we have vector multiplication means we have a vector multiplied by another vector. Two kinds of vector multiplication. The dot product is a scalar product, means vector dot vector equals scalar. So in the dot product, we have a vector dot vector equals a scalar. In the cross product, we have a vector cross a vector equals a vector. Two kinds of multiplication for vectors, the dot product and the cross product. And just like before, there are two things what we need to know about each of these operations: how to do them and what they represent. So we got 4 things to talk about over the next couple of days. Any questions? Okay. All right, one very last thing has to do with the homework. There was a homework that involved a function. Let's just use the one that I had, where it said x to the 0.3 times y to the 0.7. So the function was the form x to the alpha times y to the 1 minus alpha. So on this homework assignment, they asked for ranges of alpha, and I'm not sure what their point was. I couldn't figure out what they were going for. You might have different values, but on the problem it says what are viable ranges for alpha. For some reason, whatever numbers you're given, just answer those. The values for alpha should be strictly between 0 and 1. You could have 0.01 and then 0.99 to fit this format, and it would still be a perfectly valid, although kind of excessive, function. But for some reason, I was able to get 0.3 and 0.7. I looked at the answer, and when I had the function that said 0.3 and 0.7, it said between 0.3 and 0.7. I don't know why that is. And then someone else had a 0.2 and a 0.8, and their answer was between 0.2 and 0.8. And this is all super fishy. And I'm not sure why it's not accepting between 0 and 1. So whatever these two are, if you get a 0.4 and a 0.6, just go between 0.4 and 0.6. If you're to start off 0.6 and 0.4, make sure that they go in the right order, because then you're just being weird. If you're like, oh, 0.6 is less than alpha is less than 0.4. Now you're just like putting things in the wrong order. So just answer the question this way. I think it'll work out. And then we'll just kind of shrug at this one. All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.
Peace out, Professor.